Who will revise what we did in last lecture? Okay, nobody wants to interact, right? Okay, fine. So moving further with the next submodule, that is first law of thermodynamics. So you must have studied what is first law of thermodynamics before, even in your high school or in your 11th, 12th physics you must have studied, or not? So what is your idea about the first law of thermodynamics? Anyone? Hello, what is wrong with your class? Or you people don't want to interact? If that is the case, it will be one-way process. That I will just go on talking and nothing will happen in that case. Or should I explain from my side? You don't want to participate or you don't want to interact?
Sir,
Bolo, go ahead.
First law of thermodynamics explains that we cannot create or destroy energy, but it can only be get converted from one source to another, or one form to another in a system.
Very good, very good. So this is what just I expected from you people. So first law of thermodynamics is basically law of conservation of energy, right? And then there are different types of what you can say the statements of the first law of thermodynamics, but the idea behind all those statements is it is the law of conservation of energy all the time, right? So we know that the energy can neither be created nor be destroyed. However, we know that the one form of energy can be converted to another form of energy, right? Now moving further, let us talk about how we apply this first law for a closed system undergoing a cycle. Understand this wording, application of the first law, or how we can say what is the statement for the first law for a closed system undergoing the cycle. Now by this time you must be clear with these concepts of what is open system, closed system, isolated system, what is state, what is process path, right, and what is cycle, right? So let us look at this first law applied to a closed system undergoing the cycle. So we know this, that the transfer of heat and the performance of work may both cause the same effect in a system. I repeat, the transfer of heat may be from the system or to the system, and the performance of work may be work done by the system or on the system. Both these heat and work will cause the same effect in a system. That is what the meaning of the first bullet is. Now next, heat and work are different forms of same entity. Now you should note on this, heat and work are different forms of the same entity. I am not naming what this heat and work is. I am just saying it is some kind of entity. But here what we mention is both are different forms of the same entity, right? And we call this as energy. So heat is a form of energy, work is also a form of energy, right? And this is conserved. So the energy is conserved. We know this from the first law. So heat and work are different forms of same entity called the energy, which is conserved. Then next, energy which enters a system as a heat may leave the system as a work, or Reverse is also true, that the energy which enters the system as a work may leave as a heat. So if you have a system like this, so energy, first statement says energy entering to the system as a heat may leave as a work, or in second statement we say that the energy which enters the system as a work may leave the system as a heat. So in short, what we are trying to say is heat and work, this is heat and work, these two are interconvertible, means heat can be converted to work and work can be converted to heat. So that is what the meaning of the third statement is. Heat and work are interconvertible. Now, moving further, we'll talk about the first law applied to a closed system undergoing a cycle. Now, look at the experimental setup. This is the famous the experiment conducted by the scientist Joule. So, people call this as Joule's experiment as well. So, what is done here is you are taking an adiabatic vessel. So, this is your adiabatic vessel. Now, the moment I say adiabatic, this word indicates no heat transfer. Adiabatic vessel or adiabatic wall indicates no heat transfer, and the diathermic wall indicates the heat transfer. Right? So here we are talking about the case where there is no heat transfer taking place from the system to the surrounding, or from the system surrounding to the system, reverse also. So this is your adiabatic vessel. This one is a adiabatic vessel, and what you are doing is you are taking water inside this. So this is water inside this vessel, and there is one cap fitted at the top. This one. This is also some kind of enclosure which will not allow heat transfer to take place, right? And you are adding one thermometer to this, and there is this pulley and weight arrangement along with this paddle wheel. So that's why they call it as a paddle wheel experiment. So this is your pulley and this weight arrangement. So through this you can what you can say, give the work input to the system, and the stirrer will be operated by lowering the weight, and the moment you stir the water which is present in the vessel, naturally as the work input is given to the system, the temperature of your water will increase, right? So initially we will assume that let us say this water is at the atmospheric pressure, 1 atmospheric pressure, and the temperature of the water is let us say T1 degree C, right? And the moment you lower this weight and add work input to the system, its temperature will rise because heat is not given out of the system, right? So the temperature will rise, and let us say the rise temperature of the water is T2 degrees C. Maybe you can assume random numbers like 30 degrees C, or here it can be 40 degrees C, something like that. Now this will happen because you are lowering the weight and you are adding work to the system, right? So how to represent this on a scale? So I am taking a random plane, the XY plane, and this is our initial state of the system where the temperature was T1 and the pressure is 1 atmosphere. So you are adding the work input to the system W1-2 in process 1 to 2, and your system will acquire the next equilibrium state, which is state 2, where the temperature is T2 degrees C now. And let us say that the atmospheric pressure will remain as it is throughout. So here the pressure will remain atmospheric only throughout the process, right? Now what you have to do in second half is you have to take out this cap and allow this system, or bring this system in contact with the surroundings. Now we know that the temperature of the surrounding is lower than the temperature of the water. So allow your system to attain the another equilibrium state. So let your system or the water cool from temperature T2 to the initial temperature T1, right? So this is done in process 2 to 1, where heat is rejected by your system, means water, to the surrounding, and again by following this process you will come back to the initial state, which was 1. So here work is supplied to the system W1-2, and in this process heat is rejected by the system. right? So that's what the simple the explanation of this process. So what Joule observed in this paddle wheel experiment is all the time this is true, that whatever the work input you are supplying to the system is proportional to the heat rejected by the system while coming back to the initial state. So these two quantities or entities, that is work and heat, they are always in this relation, that work supplied is proportional to the heat rejected by the system. So this is what the observation of the Joule. He tried doing this experiment with different types of liquids here, right? And then also he found the same relationship is valid, that the work input supplied to the system is directly proportional to the heat rejected by the system, right? So this is the simple case where we have only one work interaction and one heat interaction, right? So what happens if you have n number of, let us say, work interactions and n number of heat interactions? Then you will say that summation of W means sum of all the work interactions for the cycle. Now this is cycle. The sum of all the work interactions for this cycle must be equal to, now this proportionality sign is removed and one constant is put here, capital J. This is called as the mechanical equivalent of heat, or the Joule's constant, capital J, equal into summation of Q for a cycle, means sum of all the heat interactions taking place for the cycle. So this relation is valid for a cycle, right? When you have more number of heat and work interactions, right? Now what is done is, in SI system both heat and work are measured in same unit, that is Joule or kilojoule, right? So they use the value of mechanical equivalent of heat or the Joule's coefficient J as equal to 1, and then you can rewrite this expression as summation W for a cycle is equal to summation Q for a cycle, right? So for a differential terms or in differential terms or elemental terms, you can write this kind of expression, that cyclic integral of dW must be equal to J into cyclic integral of dQ. So you can put J equal to 1 here also. Use the symbol this d cross, so that we know that this is inexact differential and not the exact differential, right? So this I already mentioned, that the value of the mechanical equivalent of it, Joule, the Joule's coefficient is 1. So once we put that value 1, you can rewrite the expression, this expression as like this. Clear? So this conclusion, how the first law is applied to a closed system undergoing a cycle, is derived based on Joule's experiment, paddle wheel experiment. So remember this, summation W for a cycle must be equal to summation Q for a cycle. This is mathematical expression of the first law of thermodynamics applied to a closed system undergoing a cycle. Now can I go to next slide?
Yes, sir.
Okay, fine. Now, first law for a closed system undergoing a change of state. Now, there are different mathematical expressions for the first law. Remember, first law for a closed system. We are talking about closed system again, undergoing a change of state. So, let us say if you have a system which is at initial state 1 and it goes to the second state or the final state 2, then how do you apply the first law for this kind of situation? And this is happening in a closed system. Remember, this is happening in a closed system. So how to do that? So if Q is the amount of heat transferred to the system, what is Q? Capital Q is the amount of heat transferred to the system. What happened to this? Okay. So if Q is the amount of heat transferred to the system, this one, and W is the amount of work transferred from the system. See the wording. Q is supplied to the system, so I can randomly say this is my system, and Q is supplied to the system, and W is work transferred from the system, so the arrow is outward. During the process, then the net energy transfer Q minus W will be stored in the system. So what remains inside the system is this Q minus W. So Q is supplied, W is given by the system. So what is stored in the system is Q minus W, right? Now, the energy in storage is neither heat nor work. Energy in storage is neither heat nor work and is given the name internal energy or simply energy of the system. So this net difference between your heat and work for a closed system like this, when Q is supplied and W is taken out, that Q minus W difference is nothing but the internal energy of your system, and it is neither heat nor work. Remember this. So it is, even though we are taking the difference of Q and W, but the quantity represented by Q minus W is not heat or not work here. So it is called as simply the internal energy of the system. Now how to represent this in graphical representation? So Q is supplied, this is your system, W is taken out, so surroundings. So you can write this expression. So Q minus W is nothing but the delta E. Now this delta E is nothing but the energy storage within the system, delta E, right? So in other form you can write Q taking on the left hand side alone, the rest all on the right hand side. So you can write this equation. Q is equal to delta E plus W. Note down these expressions. While I am explaining, you should continue noting down the expressions. Fine. So the first law applied to applied in case of closed system undergoing a change of state will be written in this form. Q is equal to delta E plus W. Now what are the components of which this delta E is made up of? We are going to talk in the next slide. So look at the right hand side. So if you have more number of heat and work interactions, then we know, just now we talked about how we summarized it in case of first law applied to a cycle. Similarly, this is also valid here, that you can write sum of all the heat interactions with the system, right? So this Q is replaced by sum of all the heat interactions with the system. Delta E will remain as it is, and sum of all the work interactions taking place with the system. So depending on sign convention, this is positive because it is done by the system, this is negative because it is done on the system. So all these sign conventions are used here, and you can write this kind of expression for multiple heat and work interactions. Now this is also applied for this change of state. The same expression is written further like this. Clear? Can I go to next slide? Now we introduced this property, the energy. We talked about the delta E in the previous slide, right? Now it is time to prove that this energy is nothing but property of a system. Now for that, what we'll do is we'll consider a system which changes its state from state 1 to state 2 by following a path represented by a capital A, and the same system will return back from state 2 to state 1, but this time we'll follow a different path, path B. It means if your system is going to state 2 and coming back to the initial state following another process, right? Your system is basically undergoing a cycle like this. So I have taken one random plane, PV plane. So this is your initial state 1, the final state 2. So this is your first half. Your system is changing state 1 to state 2 following path A, and it will come back to the initial state by following path B. So I am talking about this cycle, this one, right? So you can take another process also, the process C, right? So then in that case 1A, 2C, 2C1 will be the different cycle, right? So look at this. Now what is given by the equation 1? What is this equation 1? What is equation 1? Go to the previous slide. Just now we derived this, no? Q is equal to delta E plus W. This is applied for the system having change of state, no? Right?
Yes, sir.
So this is written considering the expression which we derived just now. So for process A, I can write QA is equal to delta EA plus WA. So this is the heat interaction in process A must be equal to the change in internal energy delta E for process A plus WA, the work interaction happening during process 1 to 2. I can write this expression for process B, correct? So write down it as it is. So this is process B. I can write QB is delta EB plus WB. Name this as equation 2. Done. Now consider the cycle 1A 2B1. So I am talking about this 1A 2B1. This cycle. Consider this cycle 1A 2B. So now for a cycle, how we apply the first law? We know this. Summation W for a cycle must be equal to summation Q for a cycle, right? So using the same terminology, I can write what is the summation of W for the cycle 1A 2B1. So it is sum of work interactions, which is WA happening in process A, WB happening in process B. This must be equal to sum of the heat interactions during process A and B. So it will be QA plus QB. So this is how equation 3 is written. Clear? Now just readjust the terms. Take the terms containing this suffix A on the left hand side and suffix B on the right hand side. Rearrange this equation 3. So I am writing QA minus WA must be equal to WB minus QB. Right? Is it clear?
Yes, sir.
Yes,
sir.
Fine. Now what I am going to do is consider equation 1, 2 and 3 together, and you can prove that the change in internal energy delta EA must be equal to minus delta EB. So you have to take these three equations together, 1, 2 and 3, and you can prove this. Can you prove this? See, this
Yes,
is
sir.
QA minus W,
Yes, sir.
right?
Delta EA, and that is minus delta EB.
Yes, sir, we can prove it.
Very good. So you are getting this expression that the change in internal energy during process A is equal to minus change in internal energy during process B, right? So this we did considering the cycle 1A to B1. Now next what I am going to do is I am going to consider this cycle 1A to C1. I just change the second path. This path B is replaced by path C. And I can prove this relation without writing any step in between. I am saying this. You can try on your own and still you will be in position to prove this. So delta EA must be equal to minus delta EC. So you can add any other process like this, D maybe. So still you will find that delta EA must be equal to minus delta ED in that case, and so on. Correct?
Yes,
Now,
sir.
if you compare these two equations, what you can say is delta EB must be equal to delta EC, right? So I am rewriting this. Delta EB must be equal to delta EC. Correct?
Yes, sir.
So what is conclusion of this? Delta EB must be equal to delta AC. So that is given in the last statement. Read this statement. So the change in internal energy between two states of a system is the same, irrespective of which path you follow. Whether you follow path B, path C, path D, or any other path for that matter, as long as your initial state and final state are same, delta E in any of the process remains same. Clear? So, is it clear?
Yes, sir. Clear.
Okay. So what we can do is, when I say delta E is same for all the process, it means I can assign some value for this delta E, or I can assign some value for the energy E at a particular state. So if I say this E is, let us say 10 joule here, any random number I am taking. So means when I'm assigning this energy at point 2 as 10 kilojoule, automatically the energy at point 1 will be fixed. Now why it is fixed? because delta E should remain same, right? Getting me or not? So let us say
Yes.
this fixed value is 5 joule. Fine. So it means irrespective of the path followed, the delta E change in internal energy, right, will be this 5 joule all the time for any other process, right? It means this property energy has definite value at the state point, right? Definite value. Now what we call this kind of property? Do we call it as a property of the system or not? Because it has got definite value at a state point. So this indicates that energy is a property of the system because it has got definite value at the state point. So this is how we prove. So in examination they will ask you prove that energy is property of the system. So what you should do is you should prove that the change in energy is same for all the process. It means these two values are fixed. Means they have definite values at state point 1 and 2. This itself indicates energy is property of the system. Now can I go to next slide?
Yes, sir.
Okay, fine. Moving further, now we'll talk about what are the different forms of stored energy. We said that delta E is nothing but the energy stored because of heat and work interaction, right? So we wrote Q minus W is equal to delta E, right? So what is the different way by which you can store that energy, or what are the forms in which the energy is stored? Delta E, right? So there are two modes of in which the energy is stored in the system. So what are those modes? One is called as a macroscopic energy mode and another is called as a microscopic energy mode. I am going to project one diagram on the right hand side. Now just look at this diagram. So what is given is you have the stream of, let us say, the fluid flowing through this passage, right? And these are the fluid particles, you can see number of fluid particles and or the molecules, and we are taking the lot of number of the molecules together, right? And then we are defining what is the mass of this bulk fluid, right? So let us say the mass of the bulk fluid may be small m, and what is the velocity with which this bulk mass is moving? So this is velocity, and not the volume. So this is velocity, right? So if I say the center of this the bulk mass is at an elevation z from the datum, assume this as a datum, right? So this is elevated by distance z, then I can write this. So the energy E of a system is made up of two components. One is the macroscopic component, means which is defined on macro level. Now this is the definition of the kinetic energy of the mass on macroscopic level. Why macroscopic? Because I am taking number of molecules together, and in macroscopic sense, what is the kinetic energy of the fluid mass at this level? This is what I am defining, right? So the kinetic energy and the potential energy represented by this bulk mass is nothing but the macroscopic representation of the energy, right? So macroscopic plus capital E is what? This is internal energy. Internal energy. So the energy which is defined at the micro level, right? Means molecular level or the atomic level, what is the energy represented? That is microscopic energy. Now you should note on this, the kinetic energy, which is the macroscopic energy, is defined by this expression, half mv square. We know this. Now this v bar indicates this is velocity and not the volume. Similarly, you can define what is the potential energy, EP. P stands for potential. So this is given by mgz, mass of the fluid mass m, acceleration due to gravity g, multiplied by the elevation where it is stored, where it is there. So this will give the potential energy of your system, right? Now how to find out what is this internal energy, or what are the components which are contributing to this internal energy which is defined on micro level? So that you will see in the next slide. Now look at the next slide. So what is happening at the molecular level is there are collisions, right? So due to collision of the molecules, due to collisions, the molecules will be subjected to this kind of phenomenon like rotation or the vibration of the molecules will take place, right? The molecules will rotate about themselves, right? So it means they have the translational kind of kinetic energy, then the rotational type of kinetic energy. They can have the vibrational energy because they are vibrating from the point where they are. Then they can have the electronic energy, the chemical energy, and the nuclear energy, right? So what we'll do is we'll assume that epsilon represents the energy of one molecule. So one molecule has the energy epsilon, right? So you can write this expression, that is the energy represented by one molecule epsilon is sum of all these energies. So energy due to translational motion, energy due to rotational, energy due to vibrational, energy due to chemical, electronic energy, and the nuclear energy, right? So if you say there are n number of such total molecules in the system, then you can find out what is the total internal energy in that case. So total internal energy, capital U, will be equal to number of molecules multiplied by the energy of a single molecule. So this is how you will write the total internal energy of your system. Now, in case of ideal gas, we know this, that the internal energy is function of temperature only. Note down this. This is based on which law? You must have studied in physics. So this is based on Joule's law, that internal energy U is function of temperature alone or temperature only. Note down this. So this expression which we started with, I'm taking this equation further in the next slide here, and then we'll introduce the expression which we have derived already, that Q is equal to delta E plus W. We derived this, right? So I am going to simplify this expression. I'm going to simplify this equation. See, our basic equation was Q is equal to delta E plus W. So delta is the energy storage stored within the system, and we said that this E is made up of the kinetic energy and the internal energy. Now we are going to simplify this. So if assume you come across a situation where the changes in kinetic energy and potential energy are negligible or simply zero. So the kinetic energy is zero, potential energy is zero. In that case, you can replace this capital E by capital U. So the total energy is replaced by the internal energy U. And if that is the case, you can write this expression. So Q is equal to delta U plus W. So E is replaced by U here. So Q is equal to delta U plus W. See, whenever we use this expression, keep in mind that the changes in kinetic energy and potential energy are neglected. Note down this somewhere. So when you write Q is equal to delta U plus W, the changes in kinetic energy and potential energy are simply neglected. Now, using the differential approach, I can write this D cross Q must be equal to D plus dW. The same expression, this expression in differential form I am writing. Right? Now intentionally I am using this cross, or you can use this kind of symbol, delta Q must be equal to dE plus delta W. Now these symbols carry their meaning. This is inexact differential, that's why D cross, and this is exact differential. So energy is property of the system, exact differential. Q and W are not property of the system, they are path function, we know this. So they are inexact differential. So use that terminology as it is. So you will write it like this, right? Now here we have neglected the changes in kinetic energy and potential energy. So what is this work made up of? So you can have the different forms of work. We have already talked about this apart from PDV work. So add all those works like this, right? Now, if we assume that there is no other work involved apart from PDV work, so these works are not there. So in that case, I can rewrite this expression further. So I can write dq is dE plus dW. This dW is replaced by PDV, and if I replace E by U, I can rewrite this equation. So dq is du plus pdV, right? And if I integrate these two equations, I can write this equation. So Q is equal to delta E plus integral pdV. and same way Q is equal to delta A plus integral PdV. So these expressions I can write. Clear? Hello.
Yes, sir. Clear.
Yes, sir.
Now, specific heat at constant volume. Now you may be knowing about all this, right? So I should not spend much time on this. So what is specific heat at constant volume? The definition is given on the screen. You can read it. So it is basically the rate of change of the specific internal energy with respect to the temperature when volume is kept constant, right? So mathematical form, how I am writing the same definition here, mathematical terms. So CV is the rate of change of internal energy with respect to the temperature when this volume is held constant, right? So I can write then what is the delta U, the change in internal energy, specific internal energy, delta U, when volume is held constant. So I am just rewriting this expression and solving it, integrating this. So you will get this equation, right? Now the first law may be written for a closed stationary system as, so you can write Q is equal to delta U plus W. So sometimes you will find that this symbol is used either delta U or is used, or sometimes they use delta U small u also. When we use delta small u, this means this is on per unit mass basis, change in internal energy. This is based on per unit mass. So Q will be also in per unit mass unit, and this W will also be in per unit mass. So if Q is given in joule, then this Q represented in this equation must be joule per kg. The same is true about W. When I am writing this type of equation, remember this, right? So otherwise you can write small q also, but that is not used widely in the thermodynamics course. So let it be q only. Thing is, you should remember this is in kilojoule per kg or joule per kg, right? So in differential form, you will write this equation: dq is du plus. Now, for a process in the absence of work other than PdV work, so this we are going to replace by PdV now. So you can write dW as PdV, and the same expression can be written in this form now. So dq is equal to du plus PdV. Now this is very useful deduction. So if I use replace this symbol by q, I can write the expression like this: dq is equal to du plus PdV. You will find in few books this symbol is used. dq is equal to du plus PdV, small q. Fine. So when the volume is held constant, what we can say is the Q for a constant volume process must give you the change in internal energy delta U for the constant volume, or Q volume Q at constant volume must be equal to, now this we already derived this, so I am just putting that expression here. So Q for a constant volume process must be equal to integral of Cv dt from with the limits t1 and t2. So you write down this expression, this one. What is the relation between this Q and this integral? Or worth noting down these two bullets. So heat transferred at constant volume increases the internal energy of the system. So heat transferred at constant volume increases the internal energy of a system. And second conclusion, or second is actually deduction, not conclusion. So the product MCV, mass into the specific heat at constant volume, MCV, this is denoted by symbol capital C to the base V. Yeah? So this capital C to the base V is called the heat capacity at constant volume, which will be given in joule per Kelvin. So we know specific heat is given in joule per kg K, but the heat capacity Cv is given in joule per K. Note down this. What?
Yes, sir.
Very good. So now next we are going to define one more property called as the enthalpy. So write down the definition of enthalpy. The enthalpy of a substance is defined by this expression, H is equal to U plus E. So sum of specific internal energy and the product of the pressure and the specific volume. So these two terms are combined together and we call it as a specific enthalpy, small h. So same expression I can write in this form also, capital H is equal to capital U plus P into V. So this is volume, this is specific volume, and this is internal energy, or total internal energy you can say, and this is the enthalpy. This is specific, per net mass basis I am writing this, per net mass basis, fine. So heat transfer in a constant pressure process involving no work other than PdV work can be written by this expression we have just now talked about in the previous slide. So I am writing dQ is dV plus PdV. So only PdV work is involved there, right? So now just arrange the terms. So what I am doing is I am taking this PdV here and writing PdV. P is taken inside the derivative. So I am writing derivative of P into V, right? And this d bar q at constant T means constant pressure process, you can say is equal to dV plus d of PV. So this PdV is replaced by d of PV, right? So then again this is a mathematical step. So I am combining these two terms together. So d of U plus PV I am writing, and just now we defined U plus PV is nothing but is specific enthalpy, small h. So substitute for this bracket small h, and you will write this dq at constant P is equal to dH. Means the heat supplied at constant pressure will cause the change in enthalpy. That's the meaning. So heat transfer in case of constant volume process will change the internal energy, and the heat transferred in the constant pressure will change the enthalpy. You must remember these. So for an ideal gas, how I define this or how I modify this equation is, so we know for ideal gas I can use this ideal gas equation, PV is equal to RT. So this term is replaced by RT, H is equal to plus RT. Now, internal energy of an ideal gas depends only on temperature. We know this, we have talked about this in the previous slide. So similarly, the enthalpy of an ideal gas will also depend on the temperature only. So that's why you should note down this functional relationship. So for ideal gas, enthalpy is function of temperature alone. Note down this. Clear? And now this is the terminology I was talking about first, the total enthalpy. So capital H is called as a total enthalpy. Small h is specific enthalpy, means per net mass. So the total enthalpy H will be product of mass multiplied by specific enthalpy mH, right? So the same expression I can write like this, H is equal to U plus PV. So this H is H by M is understood. So the specific enthalpy is per net mass basis, joule per kg is the unit for specific enthalpy. And the last line is worth noting down, heat transferred at constant pressure process increases the enthalpy of the system. Now, can I go to next slide?
Yes, sir.
Yes, sir.
Now we'll introduce what is specific heat at constant pressure. Now remember, we talked about specific heat at constant volume first. Then in between we introduced enthalpy, and now we are talking about specific heat at constant pressure. There is the reason behind why we are doing this, because we need that property enthalpy H for further discussion. That's why I introduced the enthalpy first. Now look at this. The specific heat of a substance at constant pressure, Cp. What is the definition of Cp? It is the rate of change of specific enthalpy. Now you understood why we introduced enthalpy first, because we need this here. So it is the rate of change of specific enthalpy with respect to temperature when the pressure is held constant. So this is mathematical expression. Cp is dou H by dou T at constant P. Now you can integrate this and rewrite this equation that delta H at constant pressure P will be equal to integral of Cp dt, right? And if you go to constant volume process, it was delta U at constant V is integral of Cv dt. Go back and check one or two slides back. So the first law may be written for a closed stationary system and a process in the absence of any other work apart from PDV work. So you know this. Sometimes you will find yourself irritated looking at these expressions, but you have to go through all this. So dq is du plus pdv, we know this. Now I am introducing the definition of the specific enthalpy here. H is equal to u plus pv. Now I am differentiating this expression. So I can write dh, then differentiate this du, and differentiate this. So first into derivative of second plus second into derivative of first. This is how we are doing this, and we know this du plus pdv is nothing but dq. We know this. So I am going to put dq here for this, and then vdp will remain as it is, right? So this is how the expression dq is written as dh minus vdp. This is a very important deduction. So you should remember these equations. dq is equal to du plus pdv and dq is equal to dh minus vdp, right? So u is replaced by h here, and this pdv is replaced by minus vdp, right? Again, following the same procedure when the pressure is held constant, so I can write this Q at heat transferred at constant pressure is equal to delta H at constant pressure, right? So if I integrate this equation, I can write this expression, right? I'm just putting for this delta HP from this expression. This one, I'm just putting it here. So this is kept as it is, right? This is again worth noting, these two bullets. So heat transferred at constant pressure increases the enthalpy of the system. So heat transferred at constant volume increases. Heat transferred at constant volume increases what? It increases internal energy of the system, right? And what is heat transferred at constant pressure increases? It increases enthalpy, right?
Yes, sir.
And now note down the second one. See the product MCP, we are going to use symbol capital C to the base P. So this indicates the heat capacity at constant pressure. Unit is joule per Kelvin, one and the same, similar to the previous case. Can I go to next slide?
Yes, sir.
Now the last part of the discussion, energy of an isolated system. So look at this statement. An isolated system is one in which there is no interaction of the system with the surroundings. So there is no work interaction, heat interaction taking place between system and surrounding. So that kind of system we call it as an isolated system, right? So for an isolated system, this change in energy, heat, or you can say the heat transfer dq is 0, and the work transfer is also 0. So that's why you can write dw is also equal to 0. No heat and work interaction with the surroundings, right? So it means the first law for the isolated system can be deducted like this. So dE will be equal to 0. Now why I am writing this? So you know this. dq is equal to dE plus dW. We have derived this, right? So we are saying this term is 0, this is 0, right? It means D must be equal to 0, right? And when the D must be equal to 0, implies what this implies? That E must be constant. Then and then only its derivative will be 0. No? So it means the energy of an isolated system remains constant. So the energy of an isolated system is always constant. This is what we conclude when we apply first law to an isolated system. So this is nothing but the first law of thermodynamics, right? So now can I go to next slide?
Yes, sir.
Yes, sir.
Now the perpetual motion machine of the first kind. So we'll be using this notation PMM1, perpetual motion machine of first kind. Now we know this energy is neither created nor destroyed, but it only gets transformed from one form to another form. This is known to us. Now look at these two bullets and just read the statement and try to understand what this statement implies. So first statement, there can be no machine which would continuously supply mechanical work without some other form of energy disappearing simultaneously. And if such machine exists, which is nothing but the fictitious machine, we are going to call it as perpetual motion machine of first kind. So this is a fictitious machine, or this is your imagination. So you may think about creating a machine which will not consume anything, but still it will produce the work continuously, right? Without consuming anything. So this is ideal scenario. So you may think about it, right? Then the second statement, there can be no machine which would continuously consume work without some other form of energy appearing simultaneously. So this is converse of what is written in the first statement. So there can be no machine which would continuously consume work without some other form of energy appearing simultaneously. Means you cannot produce the machine which will only consume energy and will do nothing, right? This is not possible. Now look at these two diagrams and try to connect these two statements to these two graphical representations. So this is this, and this one is from. So you cannot have an engine which will continue working and will give output W without consuming anything. It is not possible, right? Or you cannot have a machine which will only absorb work or which will only take in work and will not produce any other effect. So this is not possible. So this is perpetual motion machine of first kind is simply, you can say it is violation of the first law of thermodynamics. So if you create this kind of machine, so it will be simply violation of the first law of thermodynamics. So you understood concept of the perpetual motion machine of first kind. So similarly, we will talk about the perpetual motion machine of second kind when we talk about the second law of thermodynamics. So the machine which will violate second law of thermodynamics will be PMM2 in that case. So that is the different part of discussion. We will talk about it later on. Hello.
Yes, sir.
Yes, sir.
Now here are the limitations of the first law of thermodynamics. You should understand these thoroughly. What are the limitations of first law? Because if you understand limitations of first law, then and then you will start thinking about what next then, or why second law of thermodynamics is there. Okay. So look at the limitation first. So first law of thermodynamics does not differentiate between heat and work, and assures full convertibility of one into other, whereas full conversion of work into heat is possible, but the vice versa is not possible. So first law says that heat and work are interconvertible. So it says heat can be converted to work or work can be converted to heat, but it does not talk about whether full heat can be converted to work or full work can be converted to heat. It does not talk about. Whereas the ground reality is the heat cannot be completely converted to work. Work may be converted to heat completely, but heat cannot be converted completely into work, because heat is a low grade energy, work is a high grade energy. Right? So this is what the major limitation of the first law of thermodynamics. Now look at the second statement. Read the statement. So the first law of thermodynamics does not explain the direction of a process. Means under the condition you have been given Q and W. So without looking at the magnitude of these two, you cannot decide whether Q will be converted to W or W will be converted to Q, right? And first law do not give any idea about this. So it means first law do not talk about the direction of the process, whether the direction of transfer is like this to this or this to this. It does not talk about. It only says Q can be converted to W, W can be converted to Q, right? So the problem with the directional aspect of the process is missing in first law of thermodynamics. So such as the theoretically it should permit even heat transfer from low temperature body to high temperature body, which is not practically feasible, we know this. So heat cannot be transferred from low temperature to higher temperature without any external intervention. Do you know this or not? So if you have a cup of coffee or a cup of tea kept in the room under the influence of still air, you know that as the time advances, the tea or coffee is going to cool. But same time, your coffee or tea is not going to get heated upon. On its own, spontaneity. This word spontaneity is important. So on its own, it is not possible. So spontaneity of the process is again the limitation of the first law of thermodynamics. I hope you understood this.
Yes, sir.
Fine. Now I think we should stop now. We have covered the content what was expected to be covered in this class.